All right, let's dive into a really cool physics puzzle. We're going to explore what happens when something tries to spread out, not in a simple open space, but through a path that's incredibly complex and tangled. You know what happens when you drop ink into a glass of water, right? It just spreads. It's a smooth, predictable process we call diffusion. But what if the path wasn't so smooth? What if those ink particles had to wiggle their way through a jagged, infinitely complex maze? Would they still spread out in the same way? Or would something different happen? Well, in a simple environment, spreading is like driving down a wide open highway. It's fast, it's direct, but in a complex space, it's much more like hiking a rugged, winding mountain trail. It's jagged, it's unpredictable, and as we're about to find out, it's fundamentally slower. This strange slowdown has a name: anomalous diffusion. So what kind of space actually causes this kind of weird behavior? The culprit is a mathematical object with a seriously cool name: the fractal. And it turns out fractals pose a huge problem for the traditional tools of physics. So what exactly is a fractal? Well, imagine a shape that has a repeating pattern at every single scale. Think of a coastline. If you zoom in, you see jagged rocks. Zoom in on a rock, you see jagged crystals. Zoom in again, you get the idea. It never, ever smooths out into a simple straight line. That infinite, rugged complexity is what makes it a fractal. And hey, this isn't just some abstract math concept. Fractals are literally everywhere in the real world. They describe the tangled chains of polymers, the inside of a porous rock or a sponge, and even the path water takes as it seeps through your coffee grounds in the morning. These are all real-world mazes that particles have to navigate. And here is the real kicker. The language that physics uses to describe change, calculus, was designed for smooth, predictable things. It was built for the highway, not the jagged mountain trail. So when you try to use ordinary calculus on the infinitely crinkly edges of a fractal, the math just breaks. It can't handle it. It just doesn't work. So what do you do when your old tools are broken? Well, you invent new ones. And that is exactly what the researchers in our source paper did. They essentially set out to create a brand new mathematical language, a new kind of ruler that was specifically designed to measure a jagged fractal coastline. The difference is actually pretty simple to picture. Ordinary calculus is like using a stiff, standard ruler. It's perfect for a straight line. But this new math, which they call affect calculus, is like a flexible measuring tape. It can bend and curve to follow every single nook and cranny of a complex shape. Now, the heart of this new language is something called the F-alpha derivative. You really don't need to worry about the formula. All you need to know is what it does. It measures how things change along a fractal path. And that little alpha symbol, alpha, is the secret sauce. It represents the unique dimension, or you could say the jaggedness of that specific fractal. So the geometry is literally baked right into the math. And this is the big deal, really. Scientists now have a form of calculus that finally works on fractals. It's a custom-built toolkit that allows them to write down and actually solve the equations of motion for things moving through these incredibly complicated spaces. Okay, so now they've got this powerful new mathematical language. What are they going to do with it? Well, they're going to go right back to our original problem and rewrite the rules of diffusion for a fractal world. And that's just what they did. They took a famous and very powerful equation in physics called the Fokker-Planck equation, which is basically the master blueprint for describing diffusion, and they used their new F-alpha calculus to derive a brand new version of it. The old ordinary equation uses standard calculus for nice, smooth spaces. The new fractal equation uses their F-alpha calculus for, well, fractal spaces. The key difference is that the main mathematical operator changes from a standard derivative to this new F-alpha derivative. This means the fractal's unique geometry is now embedded directly into the laws of physics. Okay, so they built a new tool, they wrote a new equation, but what did it actually tell them? This is where we get the answer to our mystery from the beginning. All right, check out this graph. This really tells the whole story. The vertical axis shows how far the particles have spread out, and the horizontal axis is just time. Now, for normal diffusion, this would be a perfectly straight line with a slope of 1. But look at this. The line slope is clearly less than that. The spreading is happening slower than it should. This is the smoking gun, the proof of what we call subdiffusion. And get this, the slope of that line is 0.799. Now, you gotta know, In physics, when a number pops out of an experiment or a simulation that's this precise, it is almost never a coincidence. This number is a huge clue. And here is the big reveal. That number, 0.799, isn't random at all. It is an almost perfect match for 1 divided by the fractal dimension of the curve they were testing. I mean, just think about that for a second. The abstract geometric jaggedness of the path was directly telling the particles how slowly to spread out. The new math didn't just describe the slowdown, it predicted it with incredible accuracy. And this is what that weird spread actually looks like. Instead of a nice smooth bell curve that we'd normally expect, the probability distribution is all warped and peaked. It's like a unique signature, a fingerprint left behind by the fractal maze the particles had to get through. You know, the authors of the paper really summed it up perfectly themselves. They said, "We clearly see that the underlying fractal nature of space gives rise to subdiffusive behavior of the diffusing entity. It's not just an obstacle. The fractal shape itself creates a whole new type of motion." So this is a beautiful piece of theoretical physics, for sure. But you might be wondering, why does it really matter in the real world? Let's take a look. Well, this new math helps us understand and predict how things move in all sorts of messy, complex, real-world systems. It applies to how a drug might diffuse through our body's tissues, how pollutants could seep through rock deep underground, or how chemical reactions happen inside complex polymer networks. It just gives us a much more accurate model for reality. But the ultimate takeaway here is a really profound idea. We tend to think about the laws of physics as being these universal, unchanging rules. But this research shows us that geometry can be destiny. The actual shape of a space can fundamentally rewrite the physical laws that govern everything happening inside it. And that leaves us with a pretty fascinating final thought, doesn't it? If the jaggedness of a simple path can actually change the law of diffusion, what other physical rules might be secretly dependent on the complex geometries hidden all around us, just waiting for us to find the right mathematical language to finally read them?